Just to remind you, in the first episode we showed both binding and wrapping methods and how we took a grass sample as a zero measurement. In the second video we showed how crop samples were taken after 6 weeks of preservation and showed the results. The third video was about the question, can film binding really be cheaper than net binding? In this final episode, Roges, who joins us today, will share the outcomes of the forage analysis after 8 months of storage. And he explains what actually happens during the invisible preservation process behind these layers of film. So Roges, could you tell us a bit more about the results of the analysis of these two types of bales after 8 months of storage?
Well, the main and most significant difference we see is with the so-called butyric acid level. After 6 weeks of preservation, this level was exactly the same. So in this net-bound bale and this film-bound bale, there was 1.5 grams per kilogram dry matter product. But after 8 months of storage, the level of that bale, that net-bound bale, went up to 9.2, whereas with this bale, this film-bound bale, it went up till 4.9.
That's much lower, isn't it?
Absolutely. It's much lower with the film-bound bales than with the net-bound bales.
And what does that tell us?
Well, butyric acid is formed by so-called unfavorable bacteria, which are mainly active when the preservation process in the bale isn't going very well. So the preservation process in these film-bound bales went much better than in this net-bound bale.
Can you tell us a bit more about the butyric acid and the influence of well-performed baling and wrapping?
Yes, I can, but first I have to explain a bit more about the preservation process in the bale. This is carried out by bacteria which are naturally present in the bale. Well, every bale partly consists of sugar, protein, water, and in the beginning you have some oxygen in the bale. After you've baled and wrapped the bale, the aerobic bacteria get to work. These are bacteria that need oxygen. These aerobic bacteria convert the sugars with oxygen into CO2, carbon dioxide and water. This means loss of energy, read sugars and dry matter. This process continues until the oxygen is consumed. Then the anaerobic bacteria take over that don't need oxygen. They also use sugars but convert them into lactic acid and CO2. This process lowers the pH and increases the CO2 concentration. Ultimately, the preservation stops depending on the dry matter content. It stops either on the basis of the pH level, in case of a dry matter lower than 50%, so relatively wet bales, or it stops based on the concentration of CO2 in the case of a dry matter higher than 50%, so relatively dry bales. So once the preservation process is stopped, you have a very stable bale and it can be stored for months and months.
Okay, but what about those butyric acid bacteria that you told me about?
Yes, I'm going to talk about that now. You have various types of anaerobic bacteria, such as the butyric acid bacteria. And these are active when the good preservative bacteria you want, such as lactic acid bacteria, do not have the optimal conditions. So the higher the butyric acid level in the bale, the worse the preservation process went. You see this especially when the storage period is longer.
How do you ensure that especially the good bacteria are active in the bale?
It has everything to do with ensiling the bale with as little oxygen as possible. Because the faster the aerobic bacteria consume the oxygen, the sooner the anaerobic bacteria can start their work and the less energy and dry matter it costs. And the result of this test showed that this process went better in the film-bound bales than in the net-bound bales. In general, the advantages of the film-bound bales over the net-bound bales are as follows. First, more air is being pushed out of this bale. That's because in the bale chamber, you pull an airtight film around the bale. It functions like an elastic band, so it's really squeezing, pushing the air out. Secondly, because of those layers of film around this bale, it's less susceptible to damage, which is very important because if there is damage on the bale, oxygen will come in and then the bale will rot and you can't use it as a farmer. The third advantage is that a film-bound bale keeps its shape better. Every bale breathes. Film never closes 100% airtight. But the trick is that to apply the film in such a way that the air inlet is minimal. So these film layers must fit together very well and must move as little as possible. Because when that happens, air can get in and you don't want that. Because a film-bound bale is bound and wrapped very quickly, it deforms less easily than a net-bound bale.
Thank you so much, Roges. So the conclusion is clear. This film-bound bale is a better bale for less money. Better because the latest analysis shows that the preservation of this bale went better than the one bound with net. And cheaper because, as we have seen in the third episode, thanks to the IntelliWrap and 3D wrapping methods from Kuhn, you use less film. This is what it's all about in the end. Cows who are enjoying their fresh and optimally preserved forage. And that is the basis for sustainable and efficient milk production.